In our last video, we discussed the identity matrix. And so in this video, we're going to look at matrix inverses. So we know that all non-zero real numbers have an inverse, but do all non-zero matrices have an inverse? The zero matrix is just a matrix where every entry is zero. If we were to say this in more mathematically precise language, we would say if A is any matrix, is there a matrix A inverse such that A times A inverse and A inverse times A is equal to the identity matrix? You maybe can predict that this is going to be true, or we wouldn't be talking about it, but it's only true for some, not all matrices. So to introduce some vocabulary, if a matrix has an inverse, we call it invertible, pretty straightforward. If a matrix isn't invertible, we call it singular. So a singular matrix has no inverse, so it exists by itself in this sense. That's why it's called singular. Only square matrices may be invertible. All non-square matrices are singular. Regardless of their numbers, they are singular and have no inverse. Some square matrices are singular and do not have an inverse. So just because a matrix is square, well, that is a necessary component for having an inverse. It is not sufficient to have an inverse. So when we are inverting a matrix, we follow a few key steps. So first, we augment the matrix with the identity matrix. So let's say we have the matrix 1, 2, 3, 4, really straightforward. We're going to augment that with 1, 0, 0, 1. So this is our matrix A, and we augment it with the identity matrix I. We're then going to use row operations like we did in solving systems of equations with matrices to reduce the original matrix on the left side to reduced row echelon form. The matrix on the right side is the inverse matrix. So we use row operations and we'll end up with 1, 0, 0, 1. And then we'll end up with some x, y, z, w. I don't know the exact numbers that we'd get with these numbers, but once we have the identity matrix on the left, whatever matrix is on the right is the inverse of the original. So if A is singular, we will obtain a row or column of all zeros on the left and be unable to make the identity. So we might end up with something like 0, 0, 1, 0, and then something here. Or we might have 0, 0, 1, 1, and then something over here. So whenever we end up with either a row of zeros or a column of zeros, it means A is singular and has no inverse. So we're going to start off with, hold on, this is weird. So there's an equation here, but it's not displaying. All right, so I'm going to pause the recording, hopefully get this fixed and not need to redo the whole thing. So give me just one moment. All right, problem fixed. Our matrix is back and we are able to compute the inverse. So our first step is to augment the matrix. So on the next line, I'm going to write 3, 5, -6, -10, our line down the middle, then 1, 0, 0, 1. Now remember, this is our identity matrix on the right, and this is our matrix A on the left. And our goal is to make this side reduced row echelon form, which in general would be the identity if we're going to have an invertible matrix. So just to remind ourselves, this is our first row, this is our second row. And I can see that we have -6 right here and 3 here. So what I'm going to do is I'm going to keep my first row and take my second row plus 2 times my first row. That way I'll have 2 times 3 is 6, and that'll cancel out the 6. So I'm going to do plus 6 plus 10 plus 2 plus 0. And now in the next, our first row stays fixed. And our second row is 0, 0, 2, 1. But notice that I've now introduced a row of all zeros on the left. What this means is that our matrix A is singular. It has no inverse. There we go. So sometimes we can get to this step in only a couple steps, sometimes we can't. Perseverance is important when we're working with matrices. So let's do an example where I assure you there will in fact be a matrix inverse. So for B, we're once again going to start by augmenting our matrix. So we have 2, 8, 1, 0. And then we have -1, -3, 0, 1. Okay, so I can see that I can use this -1 to cancel out the 2. So I'm going to keep row 2 the same, and I'm going to have row 1 plus 2 times row 2. So 2 times -1 is -2. 2 times -3 is -6. Then this is 0, and this would be plus 2. So now on the next line, I have 0, 2, 1, 2. Our bottom row is still -1, -3, 0, 1. Guess that really should have been a black line as well. Now I can see that this is getting closer to what I'd like. Because I'd like there to be a 1 here. So I am going to do 1/2 times row 1 so that I can make the first row have a 1 in the second position. So I'm going to divide 0 by 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. And 2 divided by 2 is 1. Now we'll fill in our second row. -1, -3, 0, 1. And now I can use this 1 in the second position to cancel out the 3. So my pivot, the one that's not changing, is again row 1. And row 2, I'm going to add 3 copies of row 1. So that's plus 0 in the first spot, plus 3 in the second spot, plus 3 over 2 in the third, and then plus 3 in the fourth. So -1 plus 0 is still -1. -3 plus 3 is 0. 0 plus 3 halves is 3 halves. And 1 plus 3 is 4. And now I can come back and fill in the entries from row 1. I'm going to do 2 things in one step. So the first thing I'm going to do is I'm going to do negative row 2. So this would turn into a positive. So it would be +1, 0, -3 half, -4. And then what I'm going to do is switch row 1 and row 2. And the reason I'm switching them is because I want the row that has the +1 to be in the first position. So we'll have 1, 0, -3, 2, -4. And then we're switching both rows, so that would be 0, 1, 1 half, +1. I'm going to go back to my black marker now. And now we have to notice something. This left-hand side is now the identity matrix. We have put it into reduced row echelon form, which means this over here is the inverse of our original matrix B. So B inverse is equal to -3 over 2 minus 4, 1 half, and 1. And now I'll leave it to you as an exercise to multiply B and B inverse to check that they are in fact inverses. They should be, unless we've made a mistake somewhere, which is always possible. Humans make mistakes. But I feel pretty confident that this is in fact the inverse. And it matches the notes I had from last year. So I assume we've done it correctly again. In the next video, we are going to look at finding a shortcut to know if a matrix has an inverse without trying to find it.